So,
Okay,
yeah,
shall I introduce you first?
yes.
Okay, so welcome to another episode of Young Research of Quantum Gravity. Today we have a familiar face. We have Rishabh, who was here before talking about his master project, which was in the direction of ADM formalism. Now he will be talking about his PhD related to the SYK model and holographic relations. So I'm looking forward to it. And, yeah.
Okay. Thank you. Thank you for giving me this platform again to talk about this work. During my master's, I was working in high energy. During my PhD, I definitely shifted to condensed matter side. But with this today, I want to talk about something that I have been working very closely with my advisor, Stefan Kerhein, and another collaborator, Salvatore Manmana, on page curve and entanglement dynamics, but coming from the perspective of many body physics in particular. So let's start with this talk, and I will motivate it via the black holes, but like the more major focus will be to reproduce those and how what can we understand in the context of pure fermionic systems, say in the form of lattices. So with this, let's continue. Let's start. The concept of page curve actually comes from black holes, so it's like a very brief introduction. So a lot of you might already be familiar with it, but it's just an introduction that what is a page curve, what is the definition of it, and where does it come from. So the origins of page curve actually lies in the physics of black holes, where at t equals 0, at time equals 0, you can imagine that the black hole is prepared in a pure state, and the environment is empty. So by construction at t equals 0, the entanglement entropy, the von Neumann entropy between the black hole and the environment is 0. Then we know that black holes are not dead objects. Black holes eventually like radiate through Hawking radiation. And then the entanglement entropy starts increasing with time between the black holes and the environment again. And finally, when the black hole has completely evaporated, then again we have an empty space which is in a tensor product with the rest of the environment, and the entanglement entropy again boils down to 0. So if we plot this entanglement entropy as a function of time, this is what it looks like. And this bending down of curve is a characteristic hallmark of the page curve, which we define as the page curve, which you expect from quantum unitarity. Now, what is spectacular about this? Why is it like that much relevant, say in the context of black holes? So here, this is again on the y-axis is the entanglement entropy and the x-axis is the time. This line is the thermodynamic entropy drawn of the black hole, but that is something which we are not interested in. The orange line is the page curve that we just argued with. And then comes the Hawking's calculation, which are semi-classical calculations done on curved space-time, perturbative calculations in particular, which is an excellent agreement up to the page time. Page time is where the entanglement entropy peaks, but there is a catastrophic difference between the expected page curve and the Hawking's calculation. This is one of the in a very oversimplified way, one of the ways the infamous black hole information paradox, where there is a sharp contradiction between the two. The 2 points that I would like before jumping onto the many body picture of it, is that Hawking's semi-classical calculations are basically, it's a perturbative calculation around t equals 0. And as we will see that in the context of many body physics, which is completely detached from page curve, from black hole physics, we will see that like in the presence of entanglement, any perturbative calculation around t equals 0 cannot be naively trusted. Basically, I'm implying in the direction of that if a system has some kind of criticality that comes around right before the page time, any perturbative calculation will not be able to capture physics beyond that critical point. So with this motivation, I would now like to jump wheels completely and go to the condensed matter side, many body physics side, and try to see that what entanglement dynamics with time looks in a typical many body one-dimensional setup. So with this, let's consider what exactly is like, how is the typical behavior looks like, which people have extensively studied in the literature. The very generic behavior of many body physics, which I'm assuming they are not integrable, basically they are chaotic, is that the entanglement entropy typically grows linearly, and finally it saturates where the saturation is the volume law saturation. So basically it is proportional to the system size, or like the volume of the system. In one dimensional, it's just the system size. The semi-classical picture very much holds in typical, again, typical setups where the entanglement entropy, the generation of the entanglement entropy is basically the proportion of the particle current that exists in the system. And this is what leads to the linear growth. And the most of the systems that have been studied, you will see that like the saturation happens, but the bending down never happens. So this is what, but our purpose is to reproduce the page curve where we can get a bending down, not a saturation. With this typical setup, let's try to construct a many body physical setup where we can get the bending down. So this is our setup for the whole talk that I will now explain. So suppose that you have a one-dimensional chain. You can consider it to be spinless fermion chain. You can have a spinful fermions, whatever it is. It's a fermionic chain, one-dimensional fermionic chain, where I have an arbitrary bipartition, which motivated by the black hole setup, let's call this the system, which is like, it's a semi-infinite chain. So system is finite, and the environment is a semi-infinite chain. Again, since environment, we want to keep it very much larger than the system, we always assume that n is very, very greater than m, where n and m are the number of lattice sites in the system and the environment. Now, environment is always kept free. So there is a nearest neighbor hopping. It's a quadratic Hamiltonian, so it is always kept free. In the system too, there is a nearest neighbor hopping, but on top of that, you can actually put any interaction also into the system. In this case, I have put something like a nearest neighbor interaction, but you can put like a Fermi Hubbard, you can put any other interaction that can make the system chaotic. And then it's no longer a free chain. So it's like a chaotic setup connected to a free environment, to like put it simply. The initial state that we start with is that we have the system that is completely filled. Again, think of the pure of the black hole, which is prepared in a pure setup at t equals 0. And then the environment is kept completely empty. And then we let the time evolve this initial state where the particles start leaking into the environment. And then we see that we have a Hilbert space that is divided into, it's the tensor product of the system and the environment. So initially, by construction, the initial entanglement entropy is 0 because it's just a tensor product. And we know that the tensor product of von Neumann entropy of a tensor product is 0. Finally, since the environment is very big, eventually all particles will leak out and never to return back. So again, we get a tensor product of an empty system with the environment. And the final entropy is again 0. So we do expect a page curve dynamics in this. This is by construction, this is very much expected. But let's see how it looks. So let's consider the free chain. So let me go one step back. In this case, let's consider that the talk will focus on systems which have interaction in the system. But there is an advantage that if you consider the whole system and the environment to be free too, that this model becomes analytically tractable in the thermodynamic limit. So in the case of free chain, this is the paper that my advisor published, that if you consider like, because it's a quadratic chain, so you can have numerics done on very large system sizes, and you can actually do analytics too, that I will come in a moment. The left-hand side is the small m is the number of particles in the system at any given point of time. Capital M is the number of sites in the system. And the x-axis is basically labeled as time, which has been normalized by the system size so that you can make a sensible comparison across different systems. Now, as you can see that initially at t equals 0, the system does have all the particles are in the system, so it starts with 1. And eventually, all particles leak out to the environment, and indeed, the fraction of particles in the system goes down to 0. When this is happening, you can see that the entanglement entropy grows, peaks, and then again comes down all the way, having a page curve dynamics. Why is this? Because this will set us a reference point for the coming calculations. Here you can show that the page time where it actually the entanglement entropy maximizes, it has the volume law behavior. Basically, it is proportional to the number of sites in the system. In the value of the von Neumann entropy or the entanglement entropy at the peak value also grows as the volume law, which means that it is proportional to the system size. This is numerical evidence that I'm showing, but the whole model for the free case can actually be solved by taking something called resonant level approximation. All the details can be found in this paper, where you can actually calculate these curves analytically, and you can see that indeed this is expected in the thermodynamic limit. So this is the free case. Now in the talk, we will go to the interacting case, where I think it's a very simple reason to see that why we are interested in interaction, because we want our system to be as much chaotic and as much scrambling possible in there as possible. But this indeed sets up the analytical benchmark against what is coming. Now, we go back to the setup again, where we introduce a Hubbard type interaction. These are spinless fermions, so you can have spinful fermions too. The picture remains the same. And the nearest neighbor interaction happens. Then there is a hopping, just the particles hopping into each. And the system and the environment are coupled with this G that will play a role later in the talk. So with this, when we plot the von Neumann entropy, we again start with a fully filled system and environment. We see that for a given, for example, system size m equals 5, for different interaction potentials, we do get a page curve-like behavior. Or if you fix the, say, any potential V, interaction energy V, and change the different m's, you do see that the bending down happens and like the page curve goes down. There is a nicer way to actually plot it to see the page curve more clearly. And that is as follows, that instead of having x-axis the time, what I can do is I can choose the x-axis, I can choose as a proxy the fraction of particles that is decayed into the environment. How can I see that? Because the small m by capital M is the fraction of particles in the system. 1 minus this quantity is basically the number of particles in the environment. So at t equals 0, the small m is exactly equal to capital M. So they cancel out. So at t equals 0, there are no fraction of particles in the environment. And then it keeps growing. And eventually, then all the particles have leaked into the environment. And then you get this ratio to be 1. And then you can plot the von Neumann. So this axis, the decayed fraction of particles, is a useful proxy for time as well, but to see the page curve-like behavior. This has all been done at the level of MPS, like we have used MPS. Otherwise, like using exact diagonalization, there is no chance that we will reach 50 sites. But yeah, but we can also go to higher sizes if we wait for long. But this is the picture that we get. Now with this seems to be like a setup that is very simple to replicate. Now the question is that what do we learn in this setup? Is it just that like we can reproduce it, or is there some deeper physics that might be hidden into here? So let's go there. Let's jump that von Neumann entropy. Let's consider a generalization of that. Let's consider general Rayleigh entropies, which formula is given by this, where n is the Rayleigh parameter. There are two special cases of the Rayleigh parameter. One is the n tends to 1 limit, which is the standard entanglement von Neumann entropy. And then there is something n tends to infinity, which is also called the min-entropy, because it bounds the von Neumann from below. I just showed you the plots of the von Neumann entropy, which are very smooth analytic curves with time, going up, bending down, showing a page curve-like behavior. But now I will show you just like an ad hoc thing, and I will put that into perspective later in the talk, that what happens if I plot the min-entropy for the same setup, the same system. This is what you get. For a system size for different interaction strength, let me shift this here. For different interaction strength, this is what you get. And for given V, given interaction strength for different system sizes, again this. One thing that is striking here is the curve is no longer smooth. There is a non-analyticity, a cusp that appears in the system. And this cusp always is appearing right before the page time that I will like go in a moment. Now, what is this min-entropy? Why is the min-entropy showing such a singular behavior, while the von Neumann entropy was not showing a behavior? To put this into perspective, let's consider a concept, associated concept of something called entanglement Hamiltonian. So let's start from the basics, that if we have a system A and B, A plus B, you do an arbitrary cut A and B. You can write down the total density matrix like this. You can perform a Schmidt decomposition of that, a very standard concept in quantum information theory, where these lambda i's are the Schmidt values. So that's such that the sum of the Schmidt values is basically equal to 1. Then what you do is you trace out B, and then you are left with these Rayleigh entropies, which can be written in terms of the Schmidt coefficients, the lambdas. And the associated concept of entanglement Hamiltonian by definition is as follows, that if I trace out B, I'm left with the reduced density matrix A, which is always always positive quantity. The negative logarithm of the reduced density matrix of subsystem A is defined to be the entanglement entropy. Now, why is it relevant? So let's see. If this is my entanglement in Hamiltonian corresponding to the subsystem A, The eigenvalues are simply given by the negative logarithm of the Schmidt values or the Schmidt coefficients. These Schmidt coefficients are nothing but the eigenvalues of the reduced density matrix, something that, for example, in MPS calculations also you can extract very easily. Let's look at, we have a Hamiltonian. So the first thing we ask is that how does the ground state look like? What are the ground state properties? So the ground state, basically, that the energy has to be the lowest. The lowest ground state energy is given by the largest Schmidt value because of the negative logarithm. And this formula is nothing, it can show that, it's also known as a formula. This is nothing but the definition also of the Schmidt, of the min entropy, the n tends to infinity entropy, which means the min entropy basically. Now this is something interesting because we just found a non-analyticity in the min entropy, which is a way of saying that the ground state energy of the entanglement Hamiltonian is developing a non-analyticity with time. This is a very telltale feature of a quantum phase transition, where I'm going to. But you have to obviously ask that for this entanglement Hamiltonian, like any typical quantum phase transition, what is the associated temperature to the states of the entanglement Hamiltonian? You can show this again, like I have a backup slide if anyone is interested later, that the temperature, you can associate a fictitious temperature because this is not the real temperature of the system. You can associate a fictitious temperature to the entanglement Hamiltonian as 1 over n, where n is the Rayleigh parameter. So when n tends to infinity, the fictitious temperature becomes 0. This corresponds to the ground state of the entanglement Hamiltonian, and that is given by the min entropy. So we have an entanglement Hamiltonian whose ground state is the min entropy and fictitious temperature is 1 over n. With this, let's continue and let's see what we found. So this is the picture that we found, that the min entropy develops a non-analyticity. Now we know that min entropy is nothing but the ground state of the entanglement Hamiltonian. So let's plot the entanglement Hamiltonian spectrum. We get something like that. So the top are the eigenvalues, the ground state, the first excited, the second, the third, of the entanglement Hamiltonian, and the bottom plot is just showing the Schmidt coefficients, the largest, and these are color coded. So the largest Schmidt coefficient corresponds to the ground state energy. The second largest corresponds to the orange one, they corresponds to the first excited state. The third largest similar to the second, and blah, blah, blah. And they are related by this. Indeed, now we are plotting, and the x-axis is time. Remember, this is the proxy for time, the decade fraction of particle. We see something very interesting. As time is evolving, there happens to be a level crossing between the ground state and the first excited state. This is the definition of a quantum phase transition, where the ground state and the first excited state does a level crossing. So entanglement Hamiltonian undergoes a quantum phase transition, but in time, which is not a very regular picture, because if you have a quantum phase transition picture, you generally perturb or change the parameter of the Hamiltonian G. Here, the parameter is the time itself. That's why it's a temporal quantum phase transition. We always find in all of our things, and also in the free case, you can show that analytically in the thermodynamic limit, that the critical time at which the system undergoes this criticality always happens before the page time, where criticality implies that the semi-classical picture breaks down. Accordingly, any perturbative calculation around t equals 0 will never allow you to have access to the physics that lies beyond on the other side of the criticality, which includes the bending down of the curve. That will just not be captured at the perturbative level at all. So this is one of the insights that we get in this setup. But now the question is that why is it happening? Why is the system undergoing a criticality which leads to the breakdown of perturbative calculation happening on one side of the criticality, which is in this case the t less than critical time? So let's see that what is the physical mechanism that is going on here. Before that, this is the standard picture. If anyone of you have seen the quantum phase diagram, the typical schematic for it. In the typical schematic of it, the y-axis is the temperature. The x-axis is generally a parameter g or any parameter of the theory. You tune the parameter at 0 temperature, and if the ground state undergoes a radical shift, that is the point of quantum phase transition. That quantum phase transition leads to this FANG, a quantum critical regime, where things might be very much analytic and smooth in this, but the physics within the fan can be dictated completely by the critical time, by the criticality that lies underneath. One of the interesting things is in the high temperature cuprates, which are materials for high temperature superconductivity, there is something called the strange metallic phase that appears right above the criticality of the superconducting dome, which is not explained by, for example, the Fermi liquid theory. Now, in our picture, the associated temperature of the entanglement Hamiltonian, the fictitious temperature is 1 over n, where n is the Rayleigh parameter. The the parameter of the Hamiltonian that we are changing is not something like time independent, but it is the time itself, because time is moving on. And at one point of time, we do find that the entanglement Hamiltonian, the ground state, suddenly abruptly changes its characteristic and undergoes a level crossing with the first excited state, as seen on the left plot. And accordingly the entanglement Hamiltonian basically goes through a phase transition. Now, why does it happen? We have a fermionic chain, so this has a fixed number of particles. Basically, the Hamiltonian is respecting the particle number conservation. You can show that the entanglement Hamiltonian basically then also commutes at any given instant of time with the particle number. And at any given instant of time, the system will keep living in different symmetry sectors governed by the particle numbers. But as time moves, system starts emptying into the environment. And for example, when the first particle leaks into the environment, the two disconnected sectors, the m particle sector and the m minus 1 particle sector of the entanglement Hamiltonian, these two disconnected sectors, they start talking to each other. And exactly at the moment when these two disconnected sectors interact, they touch, is the point where the criticality emerges. At that point, then the gap between the ground state and the first excited state reduces. Accordingly, the ground state develops non-analyticity and the system undergoes a temporal quantum phase transition. So this is a picture that we are talking in terms of the particle number, but the picture is quite universal. You can have any system with a conserved charge. For example, you can consider a spin system where the magnetization can be considered to be a conserved charge of the system. And with time, if the magnetization sector is changing, exactly when the two different disconnected magnetization sectors start talking to each other, at that point, the system undergoes a quantum phase transition in time. So this is the physical mechanism. Now, of course, this is what we get in the finite numerics. The natural question again to ask is, how does the scaling looks like? So that because we are performing a finite size numerics, so naturally to expect is that how can we extrapolate to the thermodynamic limit? So this is the critical time where the criticality happens. So we have made these scaling ansatz pretty standard in the literature, that suppose that it undergoes as the system size dependence. The finite size scaling is like this. Then this is the order parameter. Remember the order parameter. Let me just quickly go back one slide. Sorry. That order parameter is basically the decayed fraction in the environment. What does it mean? Before the criticality, the order parameter is 0 because there is no particle in the environment. The criticality happens and the order parameter jumps to 1 basically because one particle has escaped into that. So this 1 minus m small m by capital M is the order parameter of the theory. It's also scales like this. And like any finite size scaling, we are only interested in around the critical point because most of the universality exists around the critical point, around the neighborhood of the critical point. And here we have three exponents, as you can see, A, B, and C. When we perform this, the top one is the order parameter, the raw data. The top row is the raw data. We have the order parameter around the neighborhood of time. So T minus Tc around to 0 is so we are drawing around that. And the min entropy, which develops non-analyticity again in the neighborhood of the critical time. We find a perfect collapse because that's what the whole point is. With the right scaling, you want to have a perfect collapse that can be extrapolated to the thermodynamic limit. We found a perfect collapse in the neighborhood of this. And the numbers that we have for different potential energies, which interaction energies are this. As you can see, to a great, within the accuracy, all the three exponents are very universal, independent of the interaction, because v equals 0 is the free case. And they all belong to the same universality class of the free system, where all of the values are around 1. But this is the finite size scaling. The next question is that there is a phase transition happening. So the natural question again to ask is, what are the critical exponents associated to the order parameter, which is a universal exponent that characterizes, for example, like Ginzburg-Landau mean field theory has order parameter exponent beta equals half. We ask the same question, that this is the order parameter in the neighborhood of the critical time. What is the critical exponent beta? This beta, this is a very standard notation in the theory of phase transitions. This beta, for example, takes the value of half for Landau Ginzburg mean field theory phase transitions, and there are different universality classes which correspond to different betas. We calculate that around the vicinity where the red is the neighborhood of after the critical time. And the later data is just to show that, of course, at later times, as you keep going away from criticality, the scaling ansatz will obviously fail. They have a deviation. And we find the value of beta to within the error bars, which I have not shown here, within the error bars to belong to 0.5, which is the same as the like a mean field exponent actually. And we do find across different interaction strength to be the same. So we have a phase transition. It is a second order phase transition where we have found the scaling exponents, which are very close to being universal and the value being 1. And we have the order parameter critical exponent, which is very close to the value of the Landau-Ginzburg mean field theory. And the interactions just don't change it, which is interesting because the moment you switch on the interaction, you are making the system basically non-integrable. Still, the non-integrability, making the system non-integrable, apparently has no connection to the type of phase transition that the system is undergoing at. Now, let's consider the thermodynamic limit. For the free case, again, analytically, you can show in the thermodynamic limit that the first non-analyticity happens exactly, the growth is exactly linear, which is also consistent with other many body physics setups, where the growth actually, initial growth is linear. We also find that in our MPS matrix product state simulations, calculations, that indeed they are also effectively linear. So what we do is we collect these points and we, on the y-axis, we put the TC, the critical time that we have collected at each of the points. And on the x-axis, there is 1 over m, where m tends to infinity is the thermodynamic limit. So 1 over m goes to 0. And the y-intercept basically tells you the thermodynamic extrapolation. Now, here's something that we have not understood, and that is like an outlook to our work. I will come to that in a moment, but I will just first tell you the pattern that what we are observing here. So suppose that just remember the G that I have always put, the coupling between the system and the environment. When the coupling is comparatively higher, because all other hopping strengths, TS and TE are set to 1, we find a very smooth linear behavior which extrapolated, it indeed goes to 0. This really also matches the free case scenario where you have more control. And this just means that the system, right at the quench, when you switched on the interaction at t equals 0, the system undergoes an instantaneous phase transition right after it. Now, you make the system weakly coupled to the environment. You reduce the value of G. You see that for intermediate strength V equals 0.8, the value, basically this value, rises somewhere around 2.6, which is again consistent with the free case. But the moment you increase the interaction suppresses the finite critical time in the thermodynamic limit and pushes it down to 0. So we have this weird interplay between V and G, where strong interactions pushes the critical value to 0, and the weaker coupling that you have, again, the weaker coupling will try to make the TC finite in the thermodynamic limit, but the stronger interaction will try to suppress it. This dependence on G is something that we have not understood. This is an observation, even in the free case, where we have more control in the more analytical control. This higher values of G is something that is still bothering us, that how exactly to resolve that. But I just wanted to put it out that this is what we are observing at least. All the results are regarding the quantum phase transitions are consistent with the free case, as I've been mentioning throughout. And same, you can do it for the decayed fraction, the order parameter basically. Instead, I here showed you the plots for the TC, but you will get the same behavior here. That stronger interactions basically drives the criticality to become instantaneous in the thermodynamic limit. So with this, I would like to conclude that the typical studies in many body physics did show a saturation, but indeed you can obtain a page curve dynamics, which, as you can see, in a very simple one-dimensional setup, you can get that. What is to be learned in this setup is that there can exist underlying temporal quantum phase transition that the system goes through, and the criticality can exist right before the page time where the bending down exists. And this happens at the level of entanglement Hamiltonian. If you're just studying the Hamiltonian system itself, you're not studying the reduced density matrix, you will never find this transition. Why is it relevant? Because this critical time divides the system into two different phases of matter, and any perturbative calculation done in one phase cannot be carried over across to the another phase of matter because it is divided by this criticality. This picture is quite universal, that as long as the entanglement Hamiltonian commutes with any observables, like there is a conserved charge picture that is in the system. So whenever the entanglement Hamiltonian is pushed from one conserved symmetry, like one symmetry sector to another, exactly at that point is the criticality that emerges. Accordingly, any semi-classical picture, including in the many body physics picture, where we saw that the entanglement generation is proportional to the particle current, that completely breaks down, because that is also based on this perturbative calculation, that completely breaks down, and that's why those calculations cannot be trusted to predict long-time dynamics in such setups. The thermodynamic critical value that we said that it completely vanishes for stronger interactions, but persists for intermediate values, this is something that we are yet to understand yet. And the natural question is that why is there such a critical dependence on this G that I showed you on the last slide? The second question is that what about the models without conserved charges? So this is again my advisor in his collaboration with Gopalakrishnan, who is at Princeton, and his PhD student, Lauren. They actually published also a paper that they indeed find similar transitions in models that do not have these conserved charges, say except energy. They find that the system also has criticality, but that criticality only emerges in the thermodynamic limit, where you have you go to the thermodynamic limit. And the final question to be asked is that, is there any connection, that is there a similar, because right now this is all analogous cases, but is there a connection to any kind of black hole information paradox, where one particular paper I would like to point out is that Takeyanagi and other people, they published in 2021 something called holographic moving mirrors, where it's like it's a CFT setup where they found a gravitational dual. The paper I think is called holographic moving mirror and page curve. And they write down the CFT setup, they write down the dual, and they exactly show that they can reproduce the page curve in a black hole setup by studying on the CFT side. Now, the good part about the CFT is that the entanglement Hamiltonian can be analytically calculated. And indeed, they do provide the stress energy tensor and all other details in their paper, but they only looked at the entanglement entropy, which they found to be very smooth, but admitting a page curve dynamics, which they, using the ADS CFT, they say that this is how you can reproduce in the black hole setup. So taking that holographic moving mirrors, I do see that like that is something which I'm also right now like just looking at it, working on it. Maybe some of you are interested in that. Is that like in this setup, since we have the stress energy tensor, we have all the details about the CFT in their paper, how to write down the entanglement Hamiltonian and how to basically to see that if that entanglement Hamiltonian, the ground state of that still undergoes some kind of phase transition. If it goes before T equals TC, that will be one of the concrete setups to connect to the black hole physics. So with this, I would like to conclude and thank you for your attention.